Good morning, sir. My name is Tabassum. My roll number is 2347A04B5. I am from Electronics and Communication Engineering Department. The subject name was Electronic Circuit Analysis and the subject code 23AC402. Heat sinks in power amplifiers. Introduction to heat sinks. Heat sinks are critical components in power amplifiers to manage excess heat. They enhance the reliability and longevity of electronic devices by preventing overheating. Understanding their function is essential for designing efficient power amplifiers. What is heat sink? A heat sink is a passive cooling device that dissipates heat generated by electronic components. It typically consists of metal with high thermal conductivity such as aluminum or copper. Heat sinks increase the surface area available for heat dissipation, promoting effective cooling. Importance in power amplifiers. Power amplifiers generate significant heat due to high current levels during operation. Without proper heat dissipation, thermal runaway can occur, damaging the amplifier. Heat sinks help maintain optimal operating temperatures, ensuring reliable performance. Types of heat sinks. There are two main types of heat sinks. One is passive and another one is active. Passive heat sinks rely on natural convection for cooling, while active heat sinks use fans. The choice of heat sink type depends on the specific application and thermal requirements. Passive heat sinks. Let's discuss about passive heat sinks. Passive heat sinks are simpler and do not require external power sources. Passive heat sinks. They are often designed with the fins or extended surface to maximize airflow. These heat sinks work well for applications with moderate heat generations. Let's discuss about active heat sinks. Active heat sinks incorporate fans or pumps to enhance cooling efficiency. They are suitable for high power applications where heat generation exceeds passive cooling limits. The additional components can increase complexity and noise but improve performance. Design considerations. The design of a heat sink must consider the thermal resistance and airflow. An optimized design ensures efficient heat transfer from amplifier to the heat sink. Factors like size, shape, and orientation significantly influence cooling effectiveness. Thermal resistance. Thermal resistance measures the heat transfer efficiency from the heat source to the environment. Thermal resistance is critical for effective heat dissipation in power amplifiers. Designers aim to minimize thermal resistance according to material selection and geometry. Now comes to material selection. Common materials for heat sinks include aluminum and copper due to their thermal properties. Aluminum and copper have good thermal properties. Aluminum is lightweight and cost effective. It can be available anywhere, making it a popular choice. And copper offers superior thermal conductivity but is heavier and more expensive. Copper have more thermal conductivity but it is more cost and more heavier than compared to aluminum. Aluminum is available in market with affordable prices. Find heat sinks. Find heat sinks are designed with protruding fins to increase surface area. They enhance convective heat transfer by facilitating airflow around the sink. The fin configuration can be optimized based on the specific cooling needs of the amplifier. Mounting techniques. Proper mounting techniques ensure effective thermal contact between the amplifier and heat sink. Thermal interference materials like thermal paste or pads can enhance heat transfer. Secure mounting prevents movement and maintains consistent thermal performances. Heatsink sizing. Heatsink size is crucial for ensuring adequate cooling for power amplifiers, and undersized heatsinks may lead to overheating and component failure. Designers use thermal simulation to determine the appropriate heatsink dimensions. Thermal simulation tools. Thermal simulation software helps to predict heat distribution and temperature rise. These tools allow engineers to optimize heat sinks designed before physical prototyping. Accurate simulation can save time and resources during the design process. Testing and validation. Testing heat sinks under actual operating condition is essential for validation. Temperature measurement help access to performance of the cooling solution. Adjustments may be needed based on test results to ensure effective cooling. Common issues. Poor thermal contact can lead to insufficient heat dissipation and overheating. Dust accumulation on heatsinks can significantly reduce their cooling efficiency. Regular maintenance is important to prevent thermal management issues. Innovations in heatsink technology. Advances in material science are leading to more efficient heatsink designs. Novel techniques such as 3D printing allow for complex geometries and optimized airflow. Innovations continue to improve the cooling performance of power amplifiers. Application in audio amplifiers. In audio amplifiers, heatsinks play a critical role in maintaining sound quality. Overheating can lead to distortion and reduces audio performance. Proper heat management ensures clarity and reliability in audio applications. Application in RF amplifiers. RF amplifiers require effective heatsinks to handle high frequency signals and power levels. Thermal stability is vital for maintaining signal integrity in RF applications. Engineers focus on robust heatsink designs for optimal RF performance. Future trends. The rise of compact and portable devices is influencing heatsink design. Engineers are exploring advanced cooling methods such as thermoelectric coolers. Future designs may integrate heatsinks with other components for improved efficiency. Conclusion. Heatsinks are indispensable for the reliable operation of power amplifiers. Understanding the design and function is crucial for engineers and designers. Effective thermal management ultimately leads to improved performance and longevity in electronic devices. Thank you.